Few human-made structures are as awe-inspiring as the Three Gorges Dam. Built by China on the Yangtze River in the heart of the country, it stands as the largest hydroelectric reservoir on Earth. This isn't just a concrete wall, it's a bold statement of modern engineering's might. Stretching 2,300 meters or 7,546 feet in length and rising 185 meters or 607 feet tall, the dam redefines what humans are capable of building on a river. From the outset, the Chinese government envisioned the project with the dual mission: to tame the Yangtze's historic floods and to power the nation with clean energy. To accomplish this, they diverted one of the world's most powerful rivers and erected a structure capable of holding 39.3 billion cubic meters, or 1,387,866,402 cubic feet of water. Every section of poured concrete marked a victory over the land's natural challenges. Around 30 billion were invested, and hundreds of thousands of workers were mobilized. Nothing was left to chance. Every step was planned with near-perfect precision. The dam's scale is staggering. It required 27 million cubic meters, or 953,496,196,001 cubic feet of concrete, enough to pave a highway all the way from Beijing to London. As an energy source, the dam operates like a colossal power station. Its 32 turbines produce 22,500 megawatts, enough to supply electricity to tens of millions of people. In just the first year of operation, the dam prevented 100 million tons of carbon dioxide from being released into the atmosphere. This made it a cornerstone of China's national effort to cut back on coal reliance. In the coming chapters, we'll explore how this dam was built, its astonishing ship elevator, and other equally or even more impressive associated structures. The ship elevator. At one end of the dam sits the world's largest and most advanced ship elevator, built to overcome a height difference of 100 meters or 328 feet. Its job is to keep river traffic moving smoothly, especially for medium-sized vessels that can't afford the long wait times of traditional locks. The system can lift ships up to 3,000 tons in just 30 to 40 minutes, an engineering feat that combines floating platforms, counterweights, pressure sensors, and automated hydraulics. Concrete walls enclose the chamber like a massive box, reinforced with metal plates to withstand water pressure and the contact of heavy machinery. Thanks to hydraulic balance, the system doesn't need to burn through massive amounts of energy to move heavy loads. Advanced sensors control every part of the process, syncing speed, pressure, and alignment to ensure a safe, steady journey. When in motion, the ship stays completely still inside the chamber, which is sealed shut by watertight gates as it rises and lowers. The liquid staircase of the Three Gorges. On the north side of the Yangtze River, where the water winds its way toward the mountains, the vast Three Gorges Dam stretches out like a stepped canal. 2 rows of locks, each made up of 5 chambers. These locks are enormous, able to hold vessels lined up across the area equal to 3 football fields. Thanks to the slope, ships can rise or fall at a height equal to a 30-story building. No pumps are needed for the system to function. Water flows in and out of each chamber naturally, pulled only by gravity through internal tunnels carved into the concrete. This design makes the system highly dependable and built to last, and it has been operating non-stop since its opening in 2003. The process runs like clockwork. A chamber fills, levels match, the gate opens, the ship moves forward, and the cycle repeats 5 times until it reaches the other side. A glass-paneled control center on the riverbank oversees it all. Just a few operators manage the sensors, gates, and water levels. What matters most is staying ahead of the flow, because what happens in one chamber can affect the rest of the system and all the ships behind it. During the rainy season, from June to September, the river's flow increases, and the locks work non-stop. Barges rise and descend slowly, as if they were pieces in a giant board game. How is it built? Building the Three Gorges Dam was no ordinary feat. It was an immense challenge against the force of the Yangtze and the limits of what humans can accomplish. China mobilized resources, technology, and labor on a scale rarely seen in history. Skilled engineers and modern machinery alone weren't enough. This project required nationwide coordination, surgical planning, and a show of brute force that defied both logic and geography. Construction officially began in 1994, though technical and environmental feasibility studies had been underway for decades. The country spent over 10 years completing the main dam, which was finished in 2006, while the final turbines weren't installed until 2012. In total, it took nearly 20 years for the entire system to become fully operational. The first major challenge was taking control of the world's 3rd longest river. To divert the Yangtze's flow and allow for dry construction, engineers designed a temporary channel and built an auxiliary dam. That initial phase involved moving millions of cubic feet of earth and rock. Once the water was redirected, the massive concrete structure began to take shape. To build the main structure, they used 27 million cubic meters, or 953,496,196,001 cubic feet of concrete. For comparison, that's enough material to construct nearly 70 skyscrapers the size of the Empire State Building. They also added around 563,000 tons of steel, enough to build 60 Eiffel Towers. At the height of the construction effort, 40,000 workers were active on site at the same time. The logistics were staggering. Internal transport systems, mobile hospitals, industrial kitchens, supply hubs, and continuous monitoring systems to prevent accidents and ensure material quality. Engineers relied on advanced technology to guarantee the dam's stability. They embedded pressure, temperature, and vibration sensors directly into the structure. To prevent the concrete from cracking due to heat while curing, they poured it in layers, which helped regulate the temperature inside such a massive volume. Much of the equipment was custom-made: heavy-duty cranes, enormous mixers, automated conveyors, and drilling machines capable of cutting through solid rock under extreme conditions. The reservoir. When the gates were closed and water began collecting behind its wall, the Three Gorges Dam reshaped the landscape entirely. The reservoir created by the dam stretches for 600 kilometers, or nearly 373 miles, from Yichang in Hubei province to Chongqing, one of the largest inland cities in China. It's essentially a new man-made version of the river. Where the Yangtze once roared with turbulence and raw energy, now there is a vast expanse of calm, jade-colored water. At its widest point, the reservoir spans 1,100 meters, or 3,608 feet, and in some areas it reaches depths of 175 meters, or 574 feet, deep enough to accommodate large ships year-round. The water level, managed with pinpoint precision, ensures stable conditions even during droughts or flood seasons, radically altering the river's historical rhythm. Before the dam, navigating the Yangtze was only possible in certain sections and at specific times of the year. Today, thanks to the reservoir, large vessels can travel uninterrupted from the inland regions all the way to the sea, unaffected by natural barriers. Shipping became faster, safer, and more efficient. With the reservoir in place, the Yangtze was transformed into a vital waterway connecting China's industrial interior to its coastal ports. The Xiaolongdi Dam. If the Three Gorges Dam showcases China's sheer strength in mastering nature, the Xiaolongdi Dam functions like its digestive system. It's less famous, less photographed, but absolutely essential. Built on the Yellow River, known for its unpredictable behavior, this dam was China's response to centuries of sediment built up that had altered the river's course, buried towns, and triggered devastating floods. Unlike the fast-flowing Yangtze, the Yellow River moves like a slow, muddy serpent. To tame it, China constructed the Xiaolongdi Dam. It doesn't impress with height or power output, but with its ability to swallow dirt and expel it with explosive force. Each year, during precisely scheduled periods, its lower gates open and unleash millions of tons of accumulated sediment in a violent horizontal blast. What bursts from its depths is water mixed with liquid earth, the river's geological memory expelled in minutes. From the dam's concrete mouths surge clouds of soil that expand like a yellow storm, clearing anything that might clog the channel. The scene is breathtaking, where the Three Gorges offers an image of calm control, of restrained and harnessed power. Xiaolongdi is the opposite, calculated fury by design. Yet nothing is left to chance. Without this dam, the Yellow River would again rise, breach its banks, and wreak havoc on the farmlands and cities that China has worked so hard to protect. Beihatan, the silent giant of the 21st century. When the Three Gorges Dam was completed, it seemed nothing could rival its sheer scale. Yet far upstream in the remote southwest, China built the towering Beihatan Dam, a project that quietly redefined what was possible. It became the second most powerful hydroelectric plant in the world, showcasing a level of technical sophistication that reflects just how much China has learned since it first tamed the Yangtze. Located in the Jinsha River, the Yangtze's main tributary, Beihatan stretches across Sichuan and Yunnan provinces, a region marked by extreme geography, seismic instability, and rugged terrain. Amid rocky gorges, Chinese engineers erected 289 meters or 948 feet high dam, making it one of the tallest in the world. Its concrete arch curves between mountains like a spear wedged into the stone. Behind it lies a reservoir with a volume equivalent to 6 million Olympic swimming pools, ready to feed a row of 16 1,000 megawatt turbines, a world record for unit capacity. Chinese technicians use 3D modeling, artificial intelligence, automated ventilation tunnels, and seismic dampening structures to allow the dam to withstand powerful earthquakes. They also installed state-of-the-art turbines that operate with exceptional precision, adjusting in real time to changing water flow conditions. Beihaitan is fully integrated into a national energy distribution network that links the southwest to coastal provinces via high-voltage transmission lines. The electricity generated by its turbines travels all the way to Shanghai, Guangzhou, and other industrial zones, powering factories, cities, and high-speed trains. The river that flows in reverse, the South-North Water Diversion Project. Controlling a river is a feat. Redirecting one is nearly mythic. After constructing concrete giants like the Three Gorges Dam on the Yangtze, the sediment-devouring Xiaolongdi on the Yellow River, and the graceful colossus of the Beihaitan on the Qinsha, China didn't stop at harnessing the power of water. It set out to move it. The South-North Water Diversion Project isn't a dam or a reservoir. It's a vast network of artificial arteries that reverses the country's natural flow, channeling water from the wet southern regions to the arid north, where hundreds of millions live and the nation's industrial centers pulse with life. Northern China has long suffered from dryness. Cities like Beijing and Tianjin, along with much of the northern plain, face chronic groundwater shortages worsened by decades of overuse. Meanwhile, the south, fed by the Yangtze and its tributaries, have seasonal surpluses of water that often led to flooding. Out of this imbalance came one of the boldest ideas of the 21st century: to build a hydraulic system that would literally carry water from one end of the country to the other, with each route stretching more than 1,000 kilometers or 621 miles. The project, first envisioned during Mao Zedong's era, is divided into 3 main routes: the eastern route, the central route, and the western route. The level of engineering is astounding. Take the central route, for instance. It cuts across 700 kilometers, or nearly 435 miles of mountainous terrain, including tunnels that pierce through the Qinling Range. The system includes purification stations, smart pumping systems, and environmental monitoring to ensure the water arrives clean and at stable pressure. This is far more than just a canal. It's a vital response, a complete reimagining of the country's water system. It's linked with major dams as part of the unified hydraulic structure. The Three Gorges stores energy and tames floods. Xiaolongdi clears sediment from the Yellow River. Beihaitan powers the future. The South-North Diversion, by contrast, is the circulatory system. The Grand Canal of China, the millennia-old liquid highway. If the Three Gorges Dam represents modern mastery over rivers, and the South-North Water Diversion Project embodies the ambition to redraw the nation's hydraulic map, then the Grand Canal of China is the ancient route that anchors both feats. Long before China built colossal dams or gravity-defying elevated canals, it had already created an unprecedented achievement, an artificial river that has connected north and south for over 1,400 years. The Grand Canal is both a historic relic and a living infrastructure, adapted and upgraded to become part of the 21st century water system. Spanning 1,700 kilometers, or 1,056 miles, it is the longest man-made canal in the world. It links the Yangtze River in the south with the Yellow River and the Hai River in the north, connecting key regions such as Hangzhou, Suzhou, Nanjing, Jinan, Tianjin, and Beijing. Construction began as separate segments during the Sui dynasty in the 7th century, but it reached its full form during the Yuan, Ming, and Qing dynasties. Since then, it has served as an economic, political, and cultural backbone for China. Today, parts of the canal have been integrated into the South-North Water Diversion Project, especially the eastern route, which relies on this ancient infrastructure to carry water from the lower Yangtze to the northern provinces. Though it now serves a modern role, the canal was an early hydraulic marvel. Its builders learned to manage changes in elevation, use locks, reservoirs, and auxiliary channels, all without electrical pumps or reinforced concrete. For centuries, it allowed the transport of grain, silk, taxes, troops, and ideas. It was the path through which power flowed from the fertile south to the administrative north. Without it, maintaining stability across such a vast empire would have been unimaginable. Even today, millions of tons of goods still move through its waters, thanks to dredged, upgraded stretches that are protected from highway and railway congestion. In recent years, China has worked to revitalize the Grand Canal, both as a transportation route and as part of its sustainable development strategy. New locks, water quality stations, ports, and real-time monitoring systems have been added. Ecological corridors, cultural parks, and integrated urban zones have also been developed along its banks. The canal no longer just connects regions, it connects eras. It's a bridge between ancient engineering and the digital hydraulics of the 21st century. The Huajian Canyon Bridge, crossing the abyss. After mastering the mighty flow of the Yangtze and building massive dams, China faced a new challenge, overcoming the barrier of its towering mountains. That's how the Huajian Canyon Bridge came to be. Located in Guizhou Province, a rugged and mountainous region, this bridge spans the deep valley of the Beipan River. It forms part of a strategic corridor that links the southwestern provinces with the economic hubs of the east. It speeds up trade, boosts tourism, and opens access to communities that were once geographically isolated. This is a structure that reshapes the landscape, and with it, the future of millions. With its deck suspended 600 meters or 1,968 feet above the canyon floor, this is the highest bridge on the planet. At that altitude, wind hits hard, and structural tolerances become razor thin. There is no room for error. Building it involved more than just assembling towers and tightening cables. It required extreme operations, hauling heavy equipment up steep slopes, drilling into solid rock, and installing steel components into high-altitude terrain. Engineers used drones, climate sensors, high-precision GPS systems, and mobile assembly platforms that allowed each segment to be installed with absolute accuracy. The anchoring towers were placed on narrow mountainsides with deep foundations designed to withstand earthquakes, powerful winds, and extreme temperature shifts. But the bridge isn't just a technical marvel, it's also a promise of progress. What once took hours to cross along winding, treacherous roads can now be done in a matter of minutes. The Yashi Expressway, a road above the clouds. The inevitable question is, how do you connect a country so vast and mountainous? How do you link entire regions of canyons, mountain ranges, and raging rivers with clockwork precision? The answer lies in a ribbon of concrete that cuts across the sky, the Yashi Expressway, a masterpiece of road engineering that connects remote places and redefines what we think of as a highway. Officially known as the Ya'an-Xichang Expressway, it winds through Sichuan Province, one of China's steepest and most seismic active regions. Its construction posed a major challenge to civil engineering. Builders had to span gorges, carve tunnels into solid rock, and erect high-altitude bridges. The result is a 240-kilometer or 149-mile highway that includes 270 viaducts and 25 tunnels, making it one of the roads with the highest proportion of elevated infrastructure anywhere in the world. Since its opening in 2012, the Yashi has earned the nickname Highway in the Air. In many sections, the asphalt quite literally floats on concrete pillars rising up 150 meters or 492 feet from the ground. The design keeps the road stable in the face of earthquakes, landslides, and extreme weather. Just as importantly, it has slashed travel time between Ya'an-Xichang from 10 hours on winding mountain roads to just 4 hours on a safe, continuous route. Beyond its logistical purpose, the Yashi Expressway signals a shift in how China tackles the challenges of its terrain. Just as the Three Gorges Dam tamed water and the Huajiang Bridge conquered the abyss, this highway overcomes mountains without destroying them. The route was planned to minimize ecological impact, with many viaducts built to protect native vegetation and preserve habitats for local species. The expressway also links with strategic corridors that reach important areas like Tibet, Yunnan, and the industrial Southwest. In this sense, it acts as an artery for regional development in historical isolated zones.